All right, so here we're doing lesson 2, conservation of energy. But before, let's quickly talk about gravitational potential energy. We've done this in grade 11, and well, we've done it a lot in grade 12 too, but we're starting it now in grade 12 in this chapter. And basically the big thing I want you to get is that H really depends on where you choose an initial point of 0 is. So what do I mean by that? Let's say we have a table. Here's a table, and I put an apple on the table. Now let's say the table is exactly 1 meter above the ground. Now you can choose the ground to be your height of 0, in which case you can calculate the gravitational potential energy of the apple to be mgh, where h is equal to 1. And that would be, well, if the apple was 1 kilogram, that's a heavy apple. But if the apple was 1 kilogram, then that would be 9.8 joules. However, you could also choose the height of the table to be 0. In which case, the gravitational potential energy of that apple is also 0. So why would you choose one over the other? Well, it depends on the problem. And here's what I mean. Let's say the problem is, well, the apple falls off the table, goes to the ground, and I want to know what speed it has before it hits the ground. Well, I might want to know how much gravitational potential energy it had on the table relative to the ground. Okay, so I would choose the ground to be h equals 0. I certainly wouldn't choose this to be h equals 0, because in this problem, the lowest point I'm going to is down here, in which case I would be calculating gravitational energy to be negative. It's still going to work in your equations, but I don't know why you'd want to do that. And however, if I had the apple and I was lifting it above the table and I was dropping it, right, and I was going to hit the table, well, then I might want to choose the table to have a height of 0. If it's never going to go past the table, then I don't need to calculate the gravitational potential here and here to have non-zero values. I may as well just set it equal to 0 here and just have one non-zero value up there. Right? So it's kind of like when you choose a coordinate system. You choose a coordinate system to make the problem as easy as possible. You could do it with other coordinate systems, just like you can place h to be 0 wherever you want and still solve the problem, but why make things harder for yourself? Okay. All right, so moving on. PowerPoint's not working. Okay, let's try the first example on the back. So this example, we have a skier rides up a 2.6 kilogram ski lift from the base of a mountain to the top. The lift is at an angle of 13.9 degrees. So here we have a lift, which is at an angle of 13.9 degrees. And it's 2.56 kilometers long. What else do we know? We know the mass of the skier. Determine the skier's gravitational potential at the top of the mountain relative to the base. So this is actually telling you where to put h equals 0. It's saying relative to the base. So it's making h equals 0 down here at the base. And we want to know what the gravitational potential right here is at the top. I'm going to label that prime because that's kind of our after point here, since we're starting down here at the bottom. Okay, let me make this bigger so we can solve the problem here. All right. So gravitational potential energy is mgh. I'm just going to call h prime because we're up the top now. Okay, and well, we need to calculate what that h is. That's not too bad. This is a right angle triangle. We know that angle and we know the hypotenuse. Right, so we can use the sine of theta equals opposite, which is our height, over hypotenuse, which is our 2.656 kilograms. Not kilograms, kilometers. Okay, 56 kilometers. Now you can rearrange to calculate h, and then you can sub that right back into this equation to get EG equals mg times, I'm going to put it into meters, so 2,560 meters times the sine of theta. All right, so now you just need to plug in your mass. So I can't remember what that is. 68.5 kilograms, and you plug in gravity, 9.81 newtons per kilogram, and you can solve for the gravitational potential energy to be 4.13 times 10 to the power of 5 joules. Okay, not a bad problem to start. Let's move on. All right, so conservation of energy. Conservation of energy at first glance is a fairly simple concept, but then I find a lot of students have trouble doing questions where you have conservation of energy. In grade 11, we like to do roller coasters a lot, and I think roller coasters are a great example because they go back and forth between gravitational and kinetic. And if you want to throw in some thermal energy there too, make it more realistic, because there is going to be some friction, unless it's some new sort of levitating coaster, which I haven't seen yet, but one day. So let's start there. So when you're attacking a conservation of energy problem, what energy says is that, well, energy cannot be created or destroyed, only converted from one type to another. So as the roller coaster goes down and back up and down, the total energy of that system remains the same. So what does that mean? It means the amount of energy here is the same as the amount of energy here, which is the same 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 here. So if you were to calculate the energy here, the total energy there, to say be, I don't know, 1,000 joules, well then the total energy here is 1,000, here it's 1,000, 1,000, 1,000, 1,000. It's always 1,000, right? Unless work is done, right, into the system. But work's not being done into the system. That's why roller coasters are so great. Sometimes they're just called gravity rides, because you just bring them to the top, right? Obviously, bringing them to the top, you have some machinery to actually put work into the system, because down here your energy is 0, and then up there it's not. So you're doing work to sort of bring your roller coaster up to the top. But then once you're at the top, right, there's no more work being done. There's a certain amount of energy in that system, and it's not going to change. Now, when you're solving a problem, right, you really have to pick 2 points. Okay, maybe I give you some information about your starting point, so that might be a good point to pick. And then maybe I want to know the speed down at the bottom. So then you'd pick this point. And you would say in your equation, total energy here equals total energy here. But maybe I didn't want to do this point. Maybe I wanted to know your speed going over the second second hill there, bump. So then maybe you pick this point. And you'd write total energy here equals total energy there. And so you just write, you can label them too. You don't have to do ET and ET prime. You can label this as point A and this point D. You can say the total energy at A equals the total energy at D. And then you'd have to look at each point separately. Okay, so what energies do we have at A? Obviously gravitational. You can choose where H is going to be 0. I might choose this to be 0 based on the lowest point. So there's definitely gravitational there. Is it moving there? Might be. So it has kinetics. Then you would say, okay, so we've got kinetic at point A and gravitational at point A. And that equals, well, here you're going to have kinetic and gravitational again. So you have kinetic at point D and gravitational at point D. What else do you have there? Is there friction as you go through the track? If there is friction as you move through the track, you've created heat. Heat that wasn't there before when you were up here, but it is there now when you're over here. So now we have also thermal energy at point D. And you just need to look at each point, figure out how much energy there is or what kinds of energy there is. And that's really the trickiest part about energy. There can be so many different kinds. And isolating them and calculating each kind can be a bit tedious. Which is why we'll talk more about momentum later. That one's a lot more practical to use in everyday scenarios. right? But that's how you set up an energy problem. And I've talked all about this. So total mechanical energy is the sum of potential and kinetic energies. Potential, I don't really like saying potential energy. I like saying stored energy. Potential sort of makes it seem like it could have energy. It's like, no, it definitely has energy. It's just stored in a certain form. It's stored in chemical bonds, or it's stored in its position in a gravitational field. Something like that. Okay? So let's say it's the total mechanical energy is the sum of kinetic energies and stored energies. Let's say that. All right, so with that, we're not going to do that. Let's talk about adding thermal energy into the problem now. So thermal energy, how are you going to calculate how much heat is produced? Well, first thinking about, well, where is it produced? Right? And most of the time when you're dealing with problems that are in motion across other surfaces, it's produced by friction. Okay, so friction is producing heat, or thermal, I shouldn't say heat, it's producing thermal energy in these situations. Okay, so how can we calculate how much thermal energy? Well, we know friction does negative work on a system because it removes energy from that system. So what we can do is we can calculate how much work friction does. And therefore we know how much energy is removed from that system. And since we know that energy removed, not necessarily removed from the whole system, you get to choose what your system is. So your system might include the train and the track, in which case, no, you're not removing it from the system because you're including the track. But it is removing it from the train's kinetic energy. Right? So we've lost kinetic energy, which is why friction does negative work. And so we have a negative value. But if we want to know how much thermal energy is produced, well, that negative amount, which was lost in kinetic, gets transferred into thermal. And since we have conservation of energy, all of it gets transferred into thermal. None is lost, none is gained. So we can say the thermal energy is just, well, that positive value, that absolute value of the work done due to friction. And we can calculate it as simply the force of kinetic friction times the total displacement of the cart, if we're still talking about the roller coaster example. Okay. Now in this case, it would be more of a distance factor than displacement, because you're not going to calculate from here to here. You want to calculate the entire length of the track that your cart was in contact with. Okay. So let's try an example with friction, a simple one, and then we'll come back to our roller coaster. All right, so we have a clerk pushes a filing cabinet of mass 22 kilograms. So someone's pushing a filing cabinet. It's great. Across the floor by exerting a horizontal force of magnitude 98 newtons. All right, so here we have someone pushing an applied force of 98 newtons. And we have a certain mass, 22 kilograms. The magnitude of the kinetic friction, so we have kinetic friction, and they give us that value. It is 87 newtons. Now it says the cabinet starts from rest, so we're going to use the law of conservation of energy again, because you can do this in other ways, to determine the speed of the cabinet after it moves. Okay, I said you could use conservation of energy, but really you can use forces and kinematics, and you can even use the work energy theorem that we did yesterday. But let's use conservation of energy. So we're going to move this from this position all the way to that position over there. Now initially it's at rest, and then over here it has some speed. Okay? And it's that speed that we're looking for. Okay, so if we're going to do conservation of energy, we need 2 points. We have to say the total energy at one point equals the total energy at another point. So what 2 points would you pick? You probably won't pick some random point in the middle. That doesn't make sense. We're going to pick the beginning and the end of where we're interested in. Okay, so let's just call this the beginning and the end. So I'll write ET equals ET prop. If you want, you can do it A and B or initial or final, your choice. Okay, so in the beginning, our total energy is what? What's our total energy? It's not moving. It's not at a certain height in a gravitational field. So what's our total energy? I don't think there's any energy there, really. Is there? Okay, 0. Okay, at the end, what do we have? Okay, at the end, well, it's moving now, so we have kinetic energy. So let's write EK. What else do we have? We have, what else did we create? Well, we created thermal energy, didn't we? Well, the friction did anyways. So let's add thermal energy. Now your next step, once you've identified all the energies present in your 2 points, is to write the equations for each one. So kinetic energy is a half mv squared, and thermal energy is times force times displacement. Now we're solving for V. And when you solve for V, you're going to come across a problem. You might already see it. Okay? You can bring this term to the other side. It's going to be negative, multiplied by 2, divided by mass, take the square root of a negative number. Something's not right there. So what happened? What went wrong? Well, let's go back and look at what we've identified here. We've identified the thermal energy that is produced. Oh. There we go. We've identified the thermal energy that is produced. Okay, that's being produced by what? That's being produced by the friction. Okay. This is obviously horizontal, so don't even bother thinking about gravitational potential because we're not rising this in a gravitational field. Okay, kinetic, there's none here, but it's in motion over here. So we've identified the kinetic energy that is present over there. All right. Hold on, let me just make this bigger. I keep forgetting to make this bigger for you. Okay. So, is there anything we've forgotten? Well, it looks like we haven't mentioned anything about this applied force. But do we need to put an applied force in an equation with energies? At first glance, it would seem, no, force isn't energies. But remember what forces do. Forces add or remove energy from a system. Right? By doing work on the system. Now, what we've done here is we've sort of put thermal energy on this side of the equation, and we've ignored the fact that friction does work. Okay, that's fine, right? Because we technically haven't ignored the fact that friction does work, right? Because the work it does is what creates that thermal energy. So we haven't ignored that at all. But what we have ignored is the work the clerk does. We've completely ignored that. Okay, so the clerk is adding work into this system. So what we have to do is not write it as 0, but write it as the work done by the clerk. FA L to D. Now, going back to friction, you don't want to think of friction as having work done and creating thermal energy. Because watch, if I were to bring this term to the other side, then I simply have the work done by the clerk subtracted the work done by the friction equals, what's this? Kinetic energy. And initially we started at 0, so technically that is change in kinetic energy. But if I had written the work done by kinetic friction here and the thermal done here, well then those two terms just, right, we have a negative term here, positive here, bring it to the other side, you're doubling up on it. Right? So you can either think of friction as doing negative work or creating thermal energy, but don't put it in the equation twice. Right? Because one thing is simply the other side of the same coin. So don't throw in 2 coins into the equation when you only have 1. Okay, but it's interesting when you look at it this way, because I can factor out a displacement. And if you want to see, you can factor out displacement, right? FA minus FK times displacement. And here you have net force. Net force times displacement is total work. Total work equaling our change in kinetic energy. So I told you you could start this this question by thinking of it as a work energy theorem. Right? Again, it's a great thing about physics. You can approach a problem from many different angles and come to the exact same place. Okay, but let's go back and so I sort of diverged there a bit. But now that we have our work done by our clerk in here, so the work done adds to the system, which gives it its kinetic energy over here, plus the thermal energy that was produced in going that far due to friction. So all that's left now is to rearrange the equation and solve for velocity. Okay, so velocity is the square root of, let's see, 2 over m times FA minus FK times displacement. I was running out of boardroom, so I did that in a step there. Right, and then you plug in all of your values, and you should get 1.1 meters per second. Okay, everyone all right with that? Now let's move on to the roller coaster question. Don't know if this is on my PowerPoint or not. Yeah, I don't think I have the same question there. All right. Last question. Here we have a cart, and you have the diagram on your sheet there. So you have a cart of mass 200 kilograms. Let's just call it M. Coasts over 5-meter tall hill traveling at 8.5 meters per second. See figure below. The cart travels 150 meters along the track and up a second hill. At what height must the second hill be so the cart just makes it over? When it says just make it over, we can assume that the velocity right at that top is going to go to 0. So there's no kinetic energy there. And it says the average force of kinetic friction is 35 newtons, so we need that too. So here we have, let me draw this. Something like that. Right? And we have a height here of 5 meters. So let's call this point A. And let's call this point B. Now point B, it says just makes it over, so we can say our kinetic energy at B is 0. Okay. Kinetic energy here is definitely not 0. So we have gravitational potential and we have kinetic. Okay. That's if you choose your base to be a height of 0. You could choose this location to be a height of 0 and simply calculate the height above here and then add another 5 meters at the end of your problem. Okay. I'm not going to do that, but it's a valid way of doing it. It's sometimes even easier to do it that way. But I'm not going to overcomplicate it just yet. Okay, so what energies do we have here? Because we're going to do the conservation of energy, which is comparing these 2 points, saying their total energies are the same. So right here we definitely have kinetic, and we have gravitational. Okay, what about right here? Don't have kinetic. I wrote plus. We don't have kinetic. We have gravitational for sure. Okay, but we also have the amount of thermal energy that was produced. So we also have thermal energy. Okay, now I don't need to add work done by something else, because in this case, there is no work done by anyone else or any other machine. It's just gravity doing the work. And you don't, just like with friction, because we include friction here as thermal energy, we don't need to include it as work done by friction. Because we include energy as a gravitational potential energy, we don't need to include energy, work done by gravity. Right? Again, two sides of the same coin. Just use the one side, whichever side you want, but don't throw in 2 coins there. All right, so once we have this set up, let's write out the equations for each. So you have half mva squared plus mgh at A equals mgh at B plus force of the force of kinetic energy times displacement. And we know all of this. It tells us the mass, it tells us the velocity at this point, it tells us the height at this point, it tells us the force of friction and the displacement. So all we have to do is rearrange that ugly equation. I'll let you do that. It's just rearranging. You're solving for the height at B. And when you do that, you get the height to be 6 meters. Any higher, it's not going to make it over. All right. See you next time.